Do you see the PowerPoint? Okay, 1 second. Now do you see it?
Yes.
Okay. So the third mode of energy transfer is by radiation. And as we have introduced last time, radiation is a heat transfer mode where heat is exchanged through electromagnetic waves. So in this case, no medium is required for heat transfer. Any surface with temperature different than 0 Kelvin can radiate or emit energy continuously in the form of electromagnetic waves due to the thermal vibrations of the molecules. When we say a surface is radiating, it's equivalent to the surface is emitting energy through a form of electromagnetic waves. Now, how to calculate the rate of radiation? We have the Stefan-Boltzmann law stating that any surface at a temperature T will emit a flux equal to epsilon, which depends on the temperature, and epsilon is the conductivity coefficient, times the Boltzmann constant, which is a universal constant, and it's equal to 5.67 times 10 to the power 8 watt per meter squared Kelvin to the power 4, times A, which is the area of the surface emitting the radiation, and T is the temperature of the surface. So we will see that radiation is the heat transfer between surfaces, and we don't need any medium between these surfaces for exchange. So even if you have vacuum, you can still have heat transfer through radiation. Now, in order to define the coefficient in radiation, we should know that we have different phenomena that can take place when a radiation hits a body. So for example here, if you look at this figure here, you have a certain flux that is incident on your surface. This is a total flux. Now, the incident flux can be divided into different parts. You can have a certain proportion that will be directly reflected. This is called phi r. You have a portion that can be absorbed by the material. This is the absorbed portion. And you have a third part that can be transmitted from the body towards the external environment. So we can say that the total flux can be divided into an absorbed, a reflected, and a transmitted portions. Okay. Now, sometimes even the absorbed portion will be radiated again. Okay. So sometimes it is stored. If it is stored by the system, then it will increase its temperature. And if it's radiated back, we can reach a certain steady state condition where the temperature of the surface will not vary anymore. And in general, when we have a steady state case, the absorbed fraction will be radiated again. This is why we will see that in the formula of radiation, the emissivity coefficient in general is equal to the absorption coefficient. And the absorption coefficient is found by the ratio of the absorbed flux over the incident flux, while the transmission ratio is the transmitted flux over the total flux, and the reflected portion rho is reflected flux over total flux. From here, since the total flux is divided into absorbed, transmitted, and radiated, if you divide this equation by the total flux, you end up with alpha plus tau plus rho equals to 1. This means that the summation of the coefficients of absorption, transmission, and reflection will be equal to 1. Now, as we said, the absorptivity is the same as the emissivity, because in steady state conditions, what is absorbed is radiated by the body again. So the rate of absorption from the environment takes place, let's say, at T equal T0, which is the temperature of the surface. Then we can say that phi absorbed is equal to the emissivity times the Boltzmann constant times A times T0 to the power 4. So the net And you know that each surface will absorb and emit, okay? So the net rate of emission from a surface at temperature T, surrounded by an environment at temperature T0, will be epsilon T times sigma times A times T4 minus T0 to the power 4. We cannot reach equilibrium until the temperature of the surface is equal to the environment temperature T0. Okay, this is why we said at steady state conditions, the portion that is absorbed will be equal to the portion that will be radiated. Any question until here? Please stop me whenever you want if you have questions.
I have a question.
Yes. Yes.
What's the difference, and why is some of the energy absorbed and some transmitted? Why isn't it all transmitted or all absorbed?
It depends on the material properties, okay? For some materials, they will not absorb anything. In this case, the emitted flux will be divided into two parts, a part that is reflected and a part that is directly transmitted. What is the difference between, you can tell me at the end if it's absorbed and then radiated back, so it's also transmitted. The difference is that when it is absorbed, so at a certain moment you have a flux that is stored inside that will tend to increase the temperature, while the transmitted flux will not change anything in the state of the material. This is the difference between transmitted and radiated, okay? So for example, we will see an example in the greenhouse effect, how the difference between absorption and transmission directly. So for example, let's say you have the solar radiation. If the atmosphere first, in the first step, will transmit directly the solar radiation. So the atmosphere will not be affected by the solar radiation that is coming through it. While when the radiation is reflected back, as we have seen before, if we have a high CO2 concentration in the atmosphere, they will block the transmission of radiation and a big portion will be absorbed. Since it is absorbed, because it's absorbed, it will try to increase the temperature. And then when it is radiated back, at the equilibrium condition, you will reach a high temperature of the atmosphere, because the absorbed portion is counted as you are gaining some heat, and then you are giving it back, okay? So there is a big difference between transmitting directly or absorbing then radiating. And you will see this in numbers when we do examples, okay?
Okay, thank you.
Welcome. Any other question? Okay. Now, an ideal absorber is defined as an object that absorbs all of the energy incident on it. So in some cases, all what is incident will be absorbed. So no reflected, no transmitted. But also when we say ideal absorber, it's an ideal reflector, okay? Because, it's an ideal object that radiates energy. Now, when we talk about zero absorption, then it is an ideal reflector because it will reflect everything. So to summarize, an ideal absorber is characterized by epsilon equal 1 because it will absorb all the energy incident to it and it will emit this energy back into a form of radiation. And it is called in this case a black body. This is why we say that an ideal absorber is also an ideal radiator of energy, because everything absorbed will be radiated back. Now, for a reflector, an ideal reflector absorbs none of the energy incident on it. So in this case, epsilon is 0, and the total proportion will be reflected back. Now, good absorber will be good radiators, while poor absorbers are poor radiators. So in general, this is why we say emissivity is equal to absorptivity. The emissivity coefficient is equal to the absorptivity coefficient, because once it will absorb, it will radiate back into the surround. And this phenomena will continue until reaching equilibrium in temperatures. Now, radiation mode is very important And one of the main application of radiation is radiant cooling. So because every object at a temperature higher than 0 will emit energy in the form of electromagnetic radiation. So we can benefit from this to cool our houses. So for example, during night, we have the external environment is at low temperature. So we can evacuate heat from the internal space through the external surfaces of our building. In general, mainly the roof, okay? So the roof can radiate towards the sky, which will be at lower temperature. And by radiation, we will cool our home. So heat is lost by long wave radiation emission from one body towards another at a lower temperature. And the other body at lower temperature is called a heat sink. In the building case, sky is the heat sink, and the building envelope is to be cooled. So as we said, in this case, the surface of the building will act as a surface of high temperature, and it will emit radiation towards the sky, which is at lower temperature. Now here we can see several techniques for cooling by radiation. One of the common techniques is to paint the roofs by white color, okay? Because the white color will absorb less energy during the day, while it will be easily cooled by radiation at night. So we should pay attention that radiation can play a negative role during the day, okay? Because we don't want during the day to radiate energy towards the home, because during the day, we have the external temperature is higher than the internal temperature, and we don't desire to have transmission of energy towards the internal space. And we know that the white color do not absorb heat a lot. So it will be an advantage to paint in white in order to avoid absorption of a high amount of energy during the day. Now, during the night, you have the temperature of the surface of the roof will be higher than the external temperature. This is why it will evacuate heat by radiation towards the sky. Now, in case we are using another technique, we like a thermal mass, for example, okay? We can cover the thermal mass of the roof by an insulating layer during the day, because during the day we don't want it to absorb the heat. So we put an insulation. And during the night, we remove the insulation in order to allow for heat transfer to the external side by radiation. Okay, now, another important topic in thermal energy is thermal insulation. You know that the construction of the building envelope plays a major role in reducing heat transfer towards the room. So in general, we like to isolate our room. So we will try to avoid interaction between the external environment and the inner space. Because, for example, in summer, we don't want heat to come in. And in winter, we don't want heat to go out of the room. So this is the role of the envelope. The envelope of the building should be resistant to heat transfer between the inner side and the outer side. So in industrialized countries, 35 to 40% of energy consumption is in buildings for heating and cooling purposes. So as you can see, we are losing a lot of energy in order to heat and cool our buildings. And as we know, there is a big trend nowadays to reduce the energy consumption, because we said that energy consumption means we are burning fuel, we are producing CO2 gases that can lead to harmful effect to global warming, and we need to avoid all of this. This is why we should try to reduce the percentage of energy consumed by our houses. So we need to consider the various thermal energy mechanisms for optimum use of energy. And one of the most important techniques is a proper construction of the building envelope. And this is done by putting several layers. So as you can see in current buildings, we are using several layers in order to increase the resistance of the envelope. So how to do this? As you can see in this figure, we can have several layers, okay? And how to calculate the resistance of a layer. We know that for conduction, if you remember last time, we have seen that the heat flux, okay, the heat flux Q dot, look, when they put Q dot, it means this this dot above the letter means the rate of change with time, because you know that the unit of Q is joule, okay, and Q dot is joule per unit time, so it's joule per second. It's equal to watt, which is power, okay. So Q dot as unit is watt. Q dot is equal for conduction to K times A times delta T, if you remember, over L. For, of course, for a certain constant conductivity in the material, we have linear variation of temperatures. This is why we can write the following expression for Q dot convection. Okay. Now we define a general form of any heat rate, which is UA delta T. And this form can be valid for conduction and can be valid for convection. Because for convection, what was the expression? Q convection, Q dot for convection is equal to H times A times delta T. So you can see that in both cases, you have area times delta T. This is a term that is common between the two. So I see here I have A times delta T, and I have here what is also A delta T. This is why I can say that I can represent any flow rate in a general form. It's A delta T times a certain coefficient. This is called, okay, this is U value. It's called the U value of the material, of a certain material. And U value can take several forms. In case of conduction, U is equal to, if you do the comparison of your terms, U will be equal in conduction to K over L. So in conduction, I can replace U by K over L. And in case of convection, I will replace U value by H. But sometimes in any process, I can have several forms of energy transfer, conduction and convection. This is why I should compute the equivalent U value. And we will learn together here how to compute the equivalent U value for any system where I have different forms of heat transfer. Okay, let us look, for example, for this simple case. This is a certain construction of a building envelope. So you have several layers of different materials. And let's say you have T1 is the temperature at the inner side, and T2 is the temperature at the outer side. You can see that here you have a certain analogy. So like in electric circuits. In electric circuits, let's say, okay, the current can try to move from one point to another. You have, if you remember from electricity, you have what is called resistance. The resistance will try to reduce the intensity of the electricity current. And here it's very similar. So by analogy, in electricity, you have the current, which is I, okay? And you have the voltage. So you have, let's say, instead of temperature, you have U1 or V1. I think you are familiar to the notation V. You have V1 and V2 from the other side. So if you are doing an electrical calculation and you want to find the current I, do you remember how we calculate I in this case?
V2 minus V1 over the sum of the resistances.
Very good, very good. So for an electric current I, it will be equal to the difference in V, so V2 minus V1 in voltage, over the resistance, the total resistance. And here, because resistance are in series, okay, then the equivalent resistance will be equal to the summation of all. So it's R1 plus R2 plus, sorry, let me fix it here. Okay. So it is R1 plus R2 plus R3, etc., plus R4. Okay. So it's now by analogy. I will clear everything so it will become clearer. Okay. So by analogy here, you can do the same thing in case of I don't know, there is a small problem. Let me fix it. Okay, so here, in case you have a flux of heat, so by analogy, the intensity is equivalent to the heat flux. Okay, your heat flux is going from the inner side to the outer side, or in the opposite direction, depending on the values of T1 and T2. If T1 is higher than T2, it will go in this direction. It will always go from the highest temperature towards the lowest temperature. Okay, so here, if you want to find the resistance of your system in the construction material, it will be equivalent to 1 over UA. Why? Because you know that in electricity you write that delta V is equal to intensity times resistance. Okay, so by analogy here, in case of heat flux, the equivalent of dV will be dt. So the temperature is equivalent to voltage, and the intensity is equivalent to the heat flux, Q dot. Okay, your heat flux, Q dot, and R is equivalent, so times this is Q times R. So what can I deduce? I can deduce, so Q dot can be written as delta T over R. If you compare these two relations, Q dot equals to UA delta T and Q dot equal to dt over R, then you can say that I can replace resistance in this system by 1 over U value times A. Okay? Now, what are the different resistances you have? In case of your building envelope, each layer will constitute a resistance. Why you should divide it into several resistances? Because you have different conductivity. Okay, for each material you have a new conductivity. This is why you can say that I can consider that I have several resistances in series. Okay, so for example here, if I have four different materials, I will take the first layer of thickness, let's say lambda 1. I will say that the resistance due to this layer is the length here, lambda, so lambda 1, over the conductivity of this layer K1 times the surface area. The same for the second and third and fourth part. And now when you want to find the total resistance, R total, you will do the summation of R1 plus R2 plus R3 plus R4. But can you tell me what is missing? I still have to add what? In addition to these resistances?
The area.
Look, I have considered conduction, but with the inner and outer space, heat transfer is by which phenomena?
Convection.
Very good, by convection. So I don't have only heat transfer by conduction through the wall, but also I have from the inner side, let's say, and from the outer side, I have heat transfer by convection. So I should add to my conduction resistances, I should add the resistance of convection from the inner side and the resistance of convection from the outer side. And I know that for convection, U is equal to what? To the coefficient of convection H. So I can say that the inner resistance is 1 over HA, because here we have R equal 1 over UA. And for convection, U is equal to H. So I deduce that R inner is 1 over H inner times A, while R outer is 1 over H outer times A. And now my total resistance will be 1 over HNA plus the summation of lambda I over KIA to take into account the several layers, plus 1 over H out times N. And in this way, I get the total resistance. And from the total resistance, I deduce the total U value, because I can say that R total is equal to 1 over U total times area. And this is what you call the U value. In general, when they give you the U value, they give you the total one for the whole system, taking into consideration convection and conduction. Any question for this? Please ask if you don't understand, I will repeat. Okay. So, okay, let us see an example how we can have the different mechanisms together. So in general, for thermal insulation, we can add one layer of air to the envelope. So one of the possible layers in your building envelope is a layer of air. And why we do this, we will see the effect of introducing an air layer. So let us consider the following example. We have a certain building envelope, and we tried several possible air layer thickness inside this envelope. Okay, so we want to design our building envelope. We have several loose material. We have concrete, let's say, we have bricks, we have several possibilities of materials, and in addition to these materials, we want to add a certain air layer in between. So let's say this is our air layer. Now, in doing the design, we should select a certain thickness of air. Okay? Do you think that increasing the thickness of the air layer will give an advantage or a disadvantage?
It will give an advantage until a certain thickness. After that, adding more thickness would be useless.
Very, very good. Why? Why we should increase for a certain thickness? What is happening?
If we compare the pink and the blue graphs,
okay, yeah. So let us do together the analysis. If you look at this figure represents the variation of heat transfer with the air layer thickness. Okay, and we know that heat transfer can take place through different mechanisms: radiation, conduction, convection, and total heat, and we can sum all of these to get the total heat transfer. Okay, now you have in blue the radiation. The radiation will not be affected by the air layer thickness. Why?
Can you repeat the question?
Okay, the radiation flux will not be affected by the air layer thickness. Why?
It's independent of the material. Yes.
Because radiation takes place at the outer surfaces. Okay?
Yes.
Radiation takes place at the outer surfaces of the envelope, not inside the envelope. Now, for the conduction, higher the air layer thickness, lower will be the conductive rate. Why? Because if you go back to the formula, what is the heat flux by conduction?
It depends on the length.
Ka times delta T over L. So higher is the thickness, lower will be the conductive flux. Okay, this is why you can see here in pink that it is reduced. Okay, the conduction rate is reduced with the increase of the air layer thickness. Now, in blue we have the convective transfer. Okay, the convective transfer here, this one. The conductive transfer will increase with air layer thickness. Why?
Because we will have a bigger area of contact.
Yeah, we will have a bigger volume where the air can do displacement. So imagine if it's very tight the motion of air will not be easy. But if you have enough space, you can move easily. Okay. So higher is the thickness. We can this allow for easier motion of air in between. Okay. This is why increasing the air layer thickness will favor convection, but it will reduce conduction. This is why we have a certain optimum, because as you can see, for the first 40 millimeter of air layer thickness, the convection increase is very small. But after 40 millimeter, it will start to increase significantly, okay? While the conduction reduction is not very high. So as you can see, the conduction reduction is very high for the first part here. And then after 40, the decrease is nearly much smaller. So when we do the summation of all fluxes, you deduce here from the black line representing the total heat transfer that nearly until reaching 50 millimeter, the total flux is reduced. But after 50, it will start to increase. This is why we say that, for example, here the optimal air layer thickness is 50 millimeters. Okay? And air is considered as a good possible layer because it's a bad conductor due to its low conductivity. Because if you remember, we said that fluids and so liquids and gases are characterized by low conductivity due to the high distances separating their molecules. And we know that mainly conduction is due to the collision between particles. This is why for air the conduction is low. Now,
Doctor?
can you give me an idea to reduce the total heat transfer through the envelope? What can we do? If you look well, the highest proportion of heat is due to what in this figure?
Conduction.
Conduction.
No, mainly radiation, especially here. After this point, the heat flux is mainly due to radiation. Because look here, if you do the summation, the highest one is radiation, then conduction, then convection. So if we can reduce radiation, it will be much easier to control the total heat transfer. Who can give me an idea to reduce radiation?
Insulation.
Insulation. We can put also a certain layer at the first surface. We can put a reflector that will reflect energy and reduce radiation flux. Okay. So let us see this in the other slide. So if we put a reflective coating on the external surface, then look, we have reduced, it was nearly 4.5 watt per meter square Kelvin, the heat transfer by radiation. When we put the reflective coating, we reduce this flux in a high amount. So it's reduced to nearly 0.5 watt per meter square Kelvin. And in this way, we will need a lower thickness of air to reduce to have optimal heat transfer, because already we have reduced a lot the total heat flux. So as you can see here in the figure, the optimal air layer thickness is nearly 30 millimeter now. So instead of 50 millimeter, we only need now 30 millimeter of air layer thickness for optimal heat transfer, because already the total heat flux is reduced. Okay? Any question for this?
The difference of the reflective coating doesn't matter, yeah?
Can you please repeat? I didn't hear you well.
We don't take into account the thickness of the coating.
The thickness of?
The coating.
The coating. The coating is very thin, very, very thin. So just you can paint with a reflective coating. It's just painting. Okay? So it's of negligible thickness.
Okay.
In case it's thick, yes, of course, you should take it into consideration. But if you are painting with a reflective material, so it will not affect the thickness of your system. Okay?
Why convection increases very slowly at first?
Sorry, I cannot hear you well. Can you please repeat?
Why convection increases very slowly at first?
Why convection increase with air layer thickness? This is the question.
I will write an
Sorry, the voice is not clear at all. Can you type it into the chatting, please? Yalla, I am waiting for you. Type it in the chat. Okay. Convection increases very slow at first because the space is still limited. Okay, so it's still a small space. So even if you increase it, air does not have the freedom of motion. But after a certain thickness, okay, it will be easier for it to do curls and to move and to have this form of motion. So to move in a circular way like this. So you need a certain minimal space to do this, okay? This is why first it increases in a very slower rate, then it will increase more, okay? So the time of the session is over, so I will send you a new link, okay?